Hello everyone, my name is Ashutosh Tiwari. I am an FPGA design engineer. I have 3.5 years of experience and I'm currently working on digital technologies. I work basically on hardware of digital national instruments and I have expertise on audio processing, image processing and wireless SDR communications in FPGA platform. So what is today's webinar trying to present? It is trying to present main how what is the role of FPGA in audio communication. Presently, the audio is a very important device in our today's communication. So we are discussing about two differential ICs. One is ADMP421, another is ADAU1761. One board belongs to Nexus A7, another board belongs to Z board. So Nexus A7 is an RTX 7 FPGA, which is a actual trainer board, and ADA 1761 is an all programmable SoC. So when it comes as an all programmable SoC, it is meant for all three applications, which is called as audio, video, and wireless. So you can use many applications like Beta Linux and PL programming, PS, all can be done in this. So the webinar is divided into two different phases. One is how you can capture the acoustic environment noise and how you can process it inside your FPGA. And another is how a Sigma DSP role, what's called as ADAU1761, what is the role of ADAU1761 and what is the I2S protocol. So coming down to the second point, MEMS microphone. Yes, what is MEMS? MEMS microphone, it's something where it converts the analog signals into electrical signals. So that is the first point. Anyone who is interested on understanding audio processing has to go through this first. So this is where we are using basically on digital cameras, Bluetooth headset, PCs, phones, and industry. So this belongs to an analog device. And today we are going to discuss on both of these ICs. So what is a pulse density modulation? So pulse density modulation is a form of modulation used to represent an analog signal in digital domain. So like I said, any analog signal can be converted into electrical signals in the phase of 0 and 1. And that analog signal is going to be captured by your DSP. So this is the mathematical form of your pulse density modulation. So you can see the level of this pulse density modulation. It has both 0 level and 1 level. So that is what it is trying to determine, the binary bit stream. So you can tell that why do I need so much zeros and ones? So zeros and ones, they are capturing the acoustic environment noise. So it will not be just 1 or 2 bit streams. It will contain n number of bit streams that will be calculated in this first equation. So this pulse density modulation modulates the audio through, it goes through a pulse coded modulation. You are converting the PDM signal to PCM signal, pulse code modulation, which represents the analog signal sampled periodically. So based on this Nyquist frequency, this is the Nyquist frequency. For PDM signals, it is trying to, for our audio band, it is trying to sample the audio signals in a Nyquist frequency. So how is this simple signal stored inside your FPGA for processing? Suppose if you want to record some audio device, how can FPGA record these values? So how do we sample these signals? So like this is an analog signal, this is a continuous signal. We are making it as a discrete signal. We are trying to change it into a discrete signal. So this analog signal is following the path of PCM encoder. This is the PCM encoder, the analog signal. This PCM encoder is trying to give you the stream of 0 and 1. So 0 bit and 1 bit. And this is the timing diagram, what you have to write inside your VHDL language or Verilog language. So the first point what we understand is that based on a clock frequency with respect to certain clock, you have to acquisite the data audio data inside your FPGA or inside your code, and you are trying to process it out somewhere. So till now, we have just discussed how the signals are converted into 0 and 1 bit stream using this timing diagram. So this is something which is used to receive the audio signal. How can we put it on the output of our FPGA? So converts an analog signal to high resolution digital stream. So what is this sigma delta modulator? Sigma delta modulator, uh, this is the first order sigma delta modulator. For every values of input, 0 and 1 input, we are making it go through an integrator, then a comparator, and it is going through a closed loop feedback. So this is a 1-bit digital to analog converter. So this is the standard diagram of first order sigma delta modulator. So your PDM signals are happening because of a 1-bit closed loop feedback sigma delta modulator. Now, we will go through each bit by bit. What is this? What is this comparator? It decides if the signal is above a particular threshold or below. So this is what the PDM signals. We are still on the PDM signals. We are not going to PWM part. Only the PDM part we are trying to compare. So we have a comparator which is trying to receive 1 bit of ADC, and we have an integrator which is performing the error quantization noise. Is shifted to high frequency. So this is the expression to analyze your sigma delta modulator, and this is the integrator. It accumulates the input signal like a memory of past samples. So we are using a D flip-flop for storage of this 1 bit, and we are going to compare it with ADC, integrator, comparator, and feedback tag. So this is the formula. I think the equation 5. This is the formula for sigma delta modulator. Now, with respect to this sigma delta modulator, once we have received 128 samples in one clock cycle, this data has to be bypassed to a PWM signal. So PWM module or port, which is called as pulse width modulation. This is pulse width modulation. We only give two values, 0 or 1. It converts the values into voltage. So you can see that based on this duty cycle, this is 10% duty cycle on, 90% duty cycle off. So this is with respect to 0.1 VDD. But when it comes to 0.5 VDD, the 50% duty cycle is on and 50% duty cycle is off. And with respect to 90% duty cycle, we are providing 0.9 VDD. So this is the representation of PWM integrator producing an output voltage by integrating the pulse stream. So what we are trying to achieve in this is we have a clock. This is the clock. And with respect to this clock, we are trying to receive or latch our data signals inside our memory. We are trying to pass this data, the pulses of train inside your pulse width modulation. So once you provide it in your pulse width modulation, this completes your audio pipeline. So from PCM, you receive some input, acoustic environment input, and you try to play it back in your output. Now, coming to Z-board, we are now discussing on Z-board. Till now, we discussed on Nexus A7. What is a Z-board? It's an all-programmable SoC. Now, it has a component or an IC from analog device, which is called as ADAU1761. It follows a protocol, I2S protocol. So what is this I2S protocol trying to achieve? Or what is this timing diagram trying to tell us? This is a communication protocol, SDA and SCA. So like I told that, in this, what we are trying to think is that there is a communication protocol, what you have to write, as a user has to write from FPGA to that IC. And based on this communication protocol and this mapping, you get the particular sequence output. So this is the DAC and this is the ADC. It requires a digital to analog converter and analog to digital converter. And this is the I2C protocol. So inside this I2C protocol, they are using I3C2. intelligent I2C controller, and they are mapping the Z board particular IC, which is called as ADAU1761 IDS. So this is with respect to clock. We are sampling the clock here, digital to analog, and here we are analog to digital converter. So from MSB to LSB, these are the particular setup time and hold time, what they have represented inside. So 8-bit clock, 12-bit of clock, 14-bit of clock, and 16-bit of clock. So with respect to how many bits you want to receive, you have to make a timing diagram with respect to that. Now, what is a fast Fourier transform, or what is DFT? We all study FFT and DFT in our classrooms, textbooks, but today's webinar is not on some analog signals. We are not performing FFT or DFT in an analog signal. We are performing FFT and DFT on PDM signals. So pulse density modulation, whatever the acoustic environment noise it is trying to grab, we are trying to go through, or we are trying to implement a fast Fourier transform, and we are trying to display it on a monitor. So we can understand that's how an audio spectrum works. So this is the first point. FFT encompasses the set of algorithms that allows for calculation efficiently the discrete Fourier transform capable of transforming a discrete signal into domain of time to domain of frequency. So when it comes to time domain to frequency domain conversion, time domain contains basically amplitude with respect to time. But we are converting it from time domain to frequency domain. So this is the frequency of the output signal. This is the formula of FFT. I guess everyone knows this formula. It is a very famous, but how can you implement it in your PDM? So how can you give your PDM input to this formula? That is what the core of webinar is today. So this is the twiddle factor. It is trying to go through 4 different rotations, 0, 90, 180, 270, and 360 degrees. So based on these trival rotations, they are going to perform an FFT output. So what we are trying to tell you is that as the PDM signal changes, the formula has to be implemented on every PDM bit. The pulse train has to go through this formula to give you an FFT output. So there is a butterfly diagram which I'll show you here. So how many stages does an FFT go through? If you have n number of stages, log with power of 2n is the number of stages what it will take. So this is the butterfly diagram what we have. This is the linear order. Suppose you have this PDM signals in a linear order. You are trying to find the mirror image of each entry. So this is how addition, subtraction, and translates back to the decimal representation of this signal, bit reversed order, linear order to bit reversed order. So in a way, what we can tell is FFT and IFFT. So suppose if my input of FFT block, this is not 1, 2, 3, 4, 5, 6, 7, 8, it's actually 0 and 1 only. As discussed, PDM is only going to give you 2 input values, 0 and 1. 0 bit stream or 1 bit stream. So based on this input, we try to send it inside an FFT block. And this FFT block is trying to give you 2 different output in linear order and output in bit reversed order. So suppose if my PDM signals are starting at this sequence, it is going through certain number of stages. So this is how the butterfly diagram is. If any questions you have, you can ask me after the webinar relating to this butterfly. Now, what is this butterfly rotation? In each FFT, the number between the butterflies represents the rotation angle. So these are the rotation angle, trival rotations from 0 to 360 degrees, like 190, 180, 270. These are the rotation angles, and these rotation angles are determined by this. Rotation of a state S is corresponds to located to the right of its butterfly, and these rotations are applied using twiddle factor. So twiddle factors are this Wn of t. This is the twiddle factor. This is the input PDM bit stream. So now we come to what is a bit reverse order and what is the difference between FFT and IFFT. The inverse fast Fourier transform implements the inverse discrete Fourier transform. So it is just rotations are in the opposite directions. So from one direction to another direction, there is just an polarity difference from FFT to IFFT. So you can see that the difference between FFT and IFFT formula, we have used 1 by n. So here the formula was, we are not using 1 by n, but we are using 1 by n on IFFT. So the rotation of this will be exactly opposite. If you do that, you get the inverse Fourier, fast Fourier transform. So what is this after the butterfly effect? What is the decimation in frequency? What is a single path delay feedback, buffer and loops? So this is the what can tell. This is the diagram of a IFFT architecture with single path delay feedback. So it requires a feedback. You can see that there is a feedback given to this. So it breaks the signal into two halves, first half and second half. Each stage does less work, fewer FFT, fewer coefficients. So decimation in frequency. And with a single part delay feedback, which inputs are paired together, butterflies mix pair of data at each stage, and buffer and flow. So in this we are using a multiplexer. So multiplexer is one way for using what can tell as a case statement. Whenever you implement a case statement, you try to implement a multiplexer. So now that FFT is completed, we are going to understand how you can perform decimation filters. There are many decimation filters like FIR filter, CIC filter, what we can implement inside this PDM signal. So what is a PDM signal? Microphone that outputs a fast 1 bit stream. 1 bit stream, a very high sampling rate, too much data to process directly. So it requires a digital signal processing or a DSP. With respect to these PDM signals, keeping only 1 out of every n samples, this will be the frequency. So yes, and this will be the Z domain representation. So you can say this formula will be the Z domain representation of your PDM signals, and this will be the formula for your impulse stream. So the decimated output back to the original input of spectrum. So these are the formulas for your impulse stream. Now, why do you need a filter? Like, why do you need a decimation filter like FIR, CIC? What is the point of having a filter? Whenever we are trying to receive a continuous signals, right? They try to go through an aliasing. This is an aliasing graph, which is trying to tell that this is removed by using a decimator filter. The true signal bandwidth doesn't change but looks stretched because the sampling rate is lower. When you decimate, it copies the spectrum overlap. Then that overlap will become as a distortion. So this overlap between these two signals ends up becoming a distortion in your audio stream. So in order to do that, we are trying to implement a low pass filter to this PDM stream before sending it to our PWM part. So it removes the frequency above. It also has a silently low pass Butterworth fourth order filter, which is trying to remove the low frequency noise or attenuate, and it is only trying to remove the high frequency noise, and only low frequencies are going inside. So this is the formula for the low pass filter, and what through our RTL we are trying to implement this FIR filter. So based on every input, we are trying to perform an FIR filter using this. So what is an FIR filter? Finite impulse response. It takes a current value with pass value and multiplies by a coefficient. So the first question what comes in our mind is that, okay, anyone can do this current plus past inputs in our RTL, but how can you get a coefficient? How are you going to determine what coefficient values are required in an FIR filter to give the output with a clear stream, right? So these coefficients can be generated using MATLAB, and there is also an IP where you can store these coefficients and you can perform an audio loopback. So first point of coefficients would be a MATLAB. Another is polyphase decomposition. Instead of one big filter, split it into n smaller subfilters. So I guess this will be the formula. This was the original for this representation. Now, with this representation, each subfilter uses every m coefficient. So in this formula, if you try to split it into smaller subfilters, you have to use every m coefficients. You have to multiply that, and it reduces from n to n divided by m. The multiplication process is getting reduced. So you only compute whenever it is necessary for a decimation. Otherwise, the switch feeds the sample to each subfilter at 1/n of rate. So this is how the PCM signal, the PDM which is converted to PCM, you can implement an FIR filter using this formula. So this is the representation of this FIR filter. And I think we can go forward. So how can you tell that your PDM signal or whatever the PCM signal you have filtered out, how is that correct? Right? So first we will require is a time domain representation of that signal to see is it correct or not. So this is the output of FIR low pass stage filter. So it removes, this is the signal originally coming from your PDM data. And this PDM data, after using our decimation filter, which means this formula, you can multiplying by coefficients, you can get a very clean and clear noise, clear audio output in your PWM. So this is something that is measured on your PWM audio stereo codec. So this is the FIR filter. Now, there are two types of filter, not just FIR filter. We also have a CIC filter. This is the output of a CIC filter, magnitude response of CIC filter. And this is the magnitude response of our FIR filter. Now, what is this CIC filter and how are you going to tell that this CIC filter is correct? So it is also a form of FIR filter, but it does not require any coefficients. So it comes up, it has two simple parts. One is the integrator and another is the combination. So it adds up the incoming samples and combination subtracts the delayed samples. Together they act like a low pass filter while decimating. So whenever they try to remove that noise, this is the formula that has to be included. So I guess you can see the Z domain representation. There are many research papers on these two CIC filter, very important in audio processing. And this is the decimation factor, differential delay, and number of stages that's doing. So this is the number of stages, stage 1 to stage 5. The stages will increase, of course, as the PDM input is increasing. So this input will be our PCM data. This PCM data goes to an integrator, downsampler, then it performs a combination and gives you a final output. So the output behavior, this will be the output behavior. So this both diagram is taken from analog device application note. So you can see that in your link. So both filters are implemented in analog device application note. The CIC output is cleaner. The first step is converting microphone PDM data into usable PCM audio. So of course, PCM audio, once the output is clear, you can send it directly to PW. Now, another aspect of this webinar, which I think I have not discussed yet, is the wireless part or wireless communication capability in an FPGA. So what is wireless and what is an RF front end of a wireless? So frequency modulation is encodes the information by shifting the carrier frequency. So for any information if you want to send by medium, it has to be encoded with a carrier frequency. And this audio signal, we are trying to receive audio signal inside our Z board and directly controls how far the carrier moves from its central frequency. So this central frequency, you can use it as a commercial radio. So if you want to utilize your FPGA as a commercial radio, you have to understand how you can configure it, right? So how much center frequency you are trying to implement and how much it has, how much gain you are trying to set, which radio station you want to listen inside your FPGA. So we have a device which is called as USRP B200. USRP B200 is an SCR transceiver. It has an RF radio frequency coverage of 70 megahertz to 6 gigahertz. So this is the coverage till 6 gigahertz. If you have some up converters, you can also increase from 6 gigahertz to millimeter wave to terahertz. So if you have a proper up converters, it can be converted into any frequency. So this is a full duplex communication happens to this. It has multiple input and multiple output. You have two TX, two RX, and the bandwidth is 56 megahertz for this. And it is only supporting USB connectivity. So through USB only, you can communicate and you can see the output. So this is the front end, this is the antenna. And from this antenna, we have mixers, low noise amplifier, programmable amplifier. From this, we have an analog to digital converter, digital to analog converter. And before you go to this baseband processing part, I would like to show the architecture of our FPGA before we do that. So this is the architecture of our B200. We have a USB connectivity device. Through USB, we have TX and RX. So of course, we have some digital up converter, digital down converter. With respect to that, we have an RFIC, RF front end switch network. The controller is, you can get the output, the antenna is connected to an SMA. There will be an SMA. So now let's go back to the part. USRP B200 has a Spartan FPGA as a processor, but it has an AD9361, an analog device, RF agile transceiver. So this is the block diagram of RF agile transceiver. If you can see, it has receiver input in differential place. So this is the differential input and this is the transmitter. So from transmitter to receiver, this is the RX channel. So you can see that it has a low noise amplifier TX RX. It requires an ADC to receive because it's an analog radio frequencies coming in an analog form. It is converting into digital, and it has multiple things that you can configure. You can configure the gain. You can implement an FIR filter in this, and with respect to that, you can give the output. So this is a built-in self-test loopback. And there is a clock oscillator. This is the clock oscillator, which is trying to set up the frequency from 70 megahertz to 6 gigahertz of RF capability. So, like I said, if the output of this is connected to a specific up converter, the frequency can be increased. This is the digital to analog converter. If the AD9361 wants to transmit something, so wideband frequency modulation is not just used for receiving audio, it's also used for transmitting something. So we are not just receiving audio, we can also send audio to your wideband frequency modulation. So this is the differential pin for this. This is the differential pin. It's not a single ended where the data is coming or going out of your FPGA. So the other end of this is Spartan 6, through which we are sending and we are receiving. So this is how the architecture of our FPGA. So with respect to this, we have a Spartan 6 FPGA which is trying to send something, receive something. So our FPGA will be the sender here, whatever we receive, and this will be the AD9361 block diagram. So transmitter and receiver channels. So any doubt on this FM, they can ask me at the end of the webinar. But this frequency modulation is necessary for higher signal to noise ratio, better interference rejection than amplitude modulation. So FM is considered as a good option than amplitude modulation, immune to amplitude variation in the channels. So this is what you can call it as an on frequency density modulation transmitter. So from front end, any binary data, it goes to an OFDM module. So this is the baseband processing from RF to IF. It receives the input are commercial radio signals. The commercial radio signals are going through this ADC and DAC. We are not using any filters for now because we have implemented filters on the RTL side. We have a DSP which is trying to give you the baseband processing. So this comes the digital front end from RF front end to digital front end. This is the typical SDR block diagram. So now I'm going to show you the demo and how in reality how these things are happening. So this is a JNU radio. This is the JNU radio what we have, and it can be also converted into Python language. It converts itself into Python language. We have a sampling frequency of 192K, and this is a USRP source. So this is the Python or USRP source. We have you can see it here. This is the terminal where you can see the device in B200. This is an ETAS USRP. We are giving an output type of 32 complex floating point number, and the channel where we are trying to receive, this is the sampling rate, what we have set here, 192K. And RF option, we are trying to receive the commercial radio signals of 95 megahertz. So the output of this can be confirmed by turning on a radio and just listening to 95 megahertz. You can tell that the code is correct. So this is the gain what we have set as 50, and we are trying to receive it on the receiver channel, second receiver channel. You can change the receiver channel here. You can change the radio frequency. You can even transmit it using wideband frequency modulation. So this is where I'm declaring my USRP that these are the things that I want. Now I have to receive. This is the block where you can receive your wideband frequency modulation. This is the sampling frequency, decimation factor, which is set as 4. And this will be the C. So it converts itself into an Python language. So you can see this is the Python code for whatever the wideband frequency modulation you have done on JNU radio. So in this way, you can user can understand it better how FPGA is controlled using JNU radio. There are multiple devices like multiple tools like LabVIEW which can be used for this. And here we are trying to see the frequency. How much frequency have we set on this? So this is the USRP frequency, central frequency, what we have set as 95 megahertz. And antenna, the gain, and the USRP sync. 48 kilohertz is the audio sync. Wideband frequency modulation is executed. So I can show the output now. So On 95 Express. Stay tuned. So you can see this is the USRP B200 what we are using. This is the USRP B210. And from USRP B210, we are trying to receive this 92 for 95 megahertz. I'm trying to receive the input from the CPU directly to your Z board. This is the CPU where you are receiving the radio streams directly as your input to your I2S. And this is where it is connected to a audio codec. This is the speaker. So from input to output, this is how a loop back is happening. So how can you convert or how can you see the DFT signals? This is the DFT signal. So this is the DFT part. And this is the time domain representation of that signal what we are receiving from our radio broadband receiver. So yes. Now coming to the coding side, how an Z board I2S protocol is implemented to receive this radio signals and why it is implemented. What is the actual functionality of this output? What is the point of having this discrete Fourier transform and getting a actual radio waves inside your FPGA? So this is necessary because it is good for acoustic audio intelligence. So someone who wants to implement artificial intelligence inside their Z board on these radio frequencies, they can get the output. So this is the code. And yes, starting with this is the VGA output of our Z board, and this has red, green, and blue component. And with this, we have this ports. So these are the ports which are used in our ADAU 1761. So you can see that these are the models that are used in this I2S. Now let us go to each block by block, to understand how you can implement this audio spectrum or to get an FFT of an radio frequency signal inside your FPGA. Now, here we are receiving an input, our Z board. It is practically a loop back, in a sense, you can tell that. But this loop back has a different features, a different outputs. We are trying to reduce our noise. We can reduce our noise through this. These are the coefficients what we have used. And through these coefficients, we can multiply with our stream of data and we can get an accumulated output. So it will going to give you a fixed and clean noise if you use this coefficient values. And from this coefficient values, whatever the filter values what we are trying to get, we try to pass it to this Z board. It gives you an output, and the output of this model is going inside the DFT processor. This is the discrete Fourier transform. So let me show you. This is the where the DFT is called. It has a magnitude calculation also. This is the DFT port. And this DFT block, we are just going to understand the architecture of IP. So this is the discrete Fourier transform, and you can see the product guide in our silence. So we are not practically doing DFT. This IP is doing DFT for us. So this is the input data bit what we are trying to give, 18 bits, and we are trying to enable the DFT output. So the configuration is very simple, and if we just know what input we can give and what magnitude calculations we have done to the calculator, imaginary and our real axis. So what is the value of imaginary value and real value, and how you try to pass it inside our FPGA. So this is a simple FSM. I think what we are using, this is written on a VHDL language, but the real application, what can be understood in this code is that if we can do DFT, we can perform first thing as noise cancellation, noise detection, and spectrum view, how you can see the spectrum, how you can understand the flow of this. Now, This is where the DFT is happening. The DFT output of the DFT, what they have provided with respect to this FPGA, we are passing it directly to our VGA module, and this VGA module is trying to give you the pattern. So there are some bar locations, like we have stored it as a read-only memory bar locations, and how much height and width of this bar should be. So bar width is low for me, but if anyone wants to change the height and width of this bar, they can do it. And through this, they try to receive the input to this FFT bar, and we try to display it directly to this Z. So now we will come back to how you can do the same process or same. Till now we were just studying about DFT, but how can you implement the same thing through Nexus A7, or how you can understand the FFT part of our Nexus A7. So yes, this is the top model where you can implement or receive the PDM signals, and you can perform an FFT on this PDM signals. So this is the spectrum processor. This is the FFT IP. So this IP has some more, what you can tell, more number of configurations, what you can see, but I will show the output before I go through this. So till then we will discuss. Yes, I think I'll do it. So yes, this is the output of our Nexus A7, and how you trying to get the PDM FFT. So this is where the mic is. This you can see everyone. This is the mic of Nexus A7. This is the mic, and for every acoustic signal that it is trying to intercept or capture, it is trying through this Nexus port, and it's trying to pass it on our mono audio output. So from PDM to PWM, there should be an RTL where it receives the signal and pass it to this output. So yes, you can see for every noise, hello, hello, for every noise you it intercepts, it's trying to give you the FFT part. This is the FFT part for this. So as soon as the frequency is increasing, and it is trying to display it accurately. So this is a real-time FFT audio spectrum which tries to perform an FFT on PDM signals. So coming back to the software. So performing an FFT is very easy in Nexus A7. It is practically giving input to this FFT ports, or FFT ports, I'm telling. The IP, you give the IP, the FFT inputs, and once the FFT is computed, it is trying to perform radix 2 like architecture. This is in this architecture, it's trying to perform the FFT. So this is the system clock, what we have given, 100 megahertz, and this is the number of channels. So this is a fixed point. You can use floating point also. And this is the scaling option, what you can use, truncation, and number of input data bits. So I think you can use it till 34, the phase factor. And linear bit are reverse bit, what I showed in the PPT. This is what the output ordering is, at what order you should get the output. And this is happening through a BRAM. So we are using configurable logic block as logic, CLB. You can use extreme DSP slices also to get the output. Now, we are just trying to give the LUTs here. These are the LUTs from 0 to 63, so 64. And we are also trying to configure that 64 in here, the transform length. This is the transform length, 64. And based on this, you directly instantiate this IP, and through this IP, whatever the output you get, you try to pass it directly to this VGA driver. And this VGA driver generates a timing signal, and on real time, it is trying for every input, whatever it is receiving, the input data, it is trying to give you the output. So for every 64 transform length, this is the dual port RAM. So like I said, it was shown as it was RAMs here. The bins will be 32 bands. So 1 to 31 is 32 bands are total that has been used in this. And we are PDM signals are received in an normal always clock. You receive the PDM data, you pass it directly to this FFT, and you get the output. So visualizer, this is the visualizer. This is the visualizer. Now, this is something with respect to FFT, but here what we are not discussing is the CIC filter, or where is CIC filter coming into this picture? Where is the loop back happening, right? So this is the last demo for this. So any questions you can ask me. So coming to this code. This is the CIC decimation filter. There are two types of filters that can be used for decimations, or what we have showed on PPT. There are many other filters like band pass filter, infinite impulse response filter that can also be implemented in our audio to get a very clean noise. And so this is the architecture for our input to output. This is the PDM data where I'm receiving with respect to a clock. I have to give a sampling clock. I have to receive my data, and I have to perform a left-right selection. This pin is meant for left-right selection. And this is the PWM signal. So this is where the output, this is something that is going out of my module inside this FPGA. So once it's going inside FPGA, it is trying to give you my audio signals in real time. So first thing happens is the single bit of data. I have a clock. I have my input here. This is a just frequency, and inside this just frequency, the mic of clock, there are 3 different frequencies that has to be generated directly for. So this is the division factor for that clock, and based on the division factor of this clock, you are trying to generate a frequency for MEMS microphone. So for this, the mic clock we are giving is 2.5 megahertz. So it is getting sampled at 2.5 megahertz for me. Yes. So where is the data getting received, and how data is getting receiving a single bit of data? So I guess this is the sampling clock, 2.5 megahertz, and this is the data mic. So it is going inside directly inside this CIC decimator. Yes, this is the CIC decimator. Yes. So very important for someone who is newly learning on audio processing is this CIC filter. How many stages are kept stages as 4, and total 64 decimation ratio is there. And for every single input, it is trying to, it will accumulator will go this much width. This is the accumulator's width and number of watts that are getting out. So output width is 17 down to 0, 18 bits directly output. That is the PCM output, 18-bit sign valid at each stage of clock. Now, whenever the rising edge of clock I am receiving, this is the rising edge of clock, and when the clock mic is high, so when my 2.5 megahertz is high and data mic is high, you are trying to receive it as signed and unsigned. So 1 and -1. So for every positive polarity, I'm storing it here, and for every negative also, I'm storing it in the same part. This is the integrator module. This is the integrator module where you are trying to perform the integrator chain. So everyone remembers from the PPT what I shared, how the integrator is used in a CIC filter. So this is a basic for loop. Yeah, I guess everyone can see that. It's just a basic for loop and present and past. So I minus 1 PDM signed value, which is coming inside this, it is directly going inside our integrator. So from integrator, what happens is from integrator, you have to send it to your combinational part, the stages of our combination. So this is the stages of my combination. For every combination output, again, we are performing a subsequent combined stages. And same approach, we are trying to give the output through the combination output. So you can see that there is no coefficients that are used in this, and directly the conversion is happening, and truncatedly it is going up. So how is the output truncation happening? Internal width is 25, output is 18 bits. 7 LSBs are rounding by adding the MSB on the top portion. So this is where CIC is getting out. We are performing the CIC with combination and integrator. Now, the output of this has to go through a delta sigma modulator. But before that, we have used a volume, auto volume. This volume is used based on the gain. So this was referred using a university paper. And based on that university paper, this code is trying to display the output. So the range of the output will be 2 power 18 and minus 2 power 18. Saturation is happening for both negative and positive buffer. So once the saturation is completed, it's going out from the volume. Volume is getting enhanced. The volume is getting out. And we are performing a reverb module. So this is the reverb module. And it is also just trying to use it as a storage, as a simple DRAM where you can store your data to the signed value. And this is the delta sigma modulator. This is the actual delta sigma modulator, which has been implemented on VHDL language. So you can see that the construction of the signal, before reconstruction, we are passing it to 2 FIR filters, int FIR1 and int FIR2. So this int FIR1 contains the coefficient values. These are the coefficient values which are multiplied on real-time pulse-coded modulation audio signals. So this is the coefficient values. These coefficient values are multiplied directly with our data value, and these data values are going out. So you can see that the values are getting out, and finally, the output of each FIR filter 1 is going inside input of FIR2. So this also contains a different coefficient filters. These are coefficient values which are multiplied with your coefficient values which are multiplied by your PCM signal. And this multiplied output goes through a delta sigma modulator. This is the delta sigma modulator. So the saturation is happening at the range of 2 power 17 and minus 2 power 17. And with respect to that, there is a delay, and you can use it as a delta sigma modulator. So this is all happening with respect to certain clock, which is the system clock for us. And this value is going directly in your output model. So the audio output, the DAC output, digital to analog, the modulator output is directly going inside the audio out, and this audio out is giving you directly to the PWM, means it's going inside your FPGA. So coming to the demo, so hello, 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 hello. So you can see from my mic data, you are also seeing the switches. These are the switches which is on based on the switch level input. Whatever the mic value is receiving, this mic value is giving you the output directly to your speaker. So this is the speaker which is giving the output. And hello, this is how basically any laptop, mobile, TV, and another mics, ADMP421 is missing. So any questions regarding this webinar? Mm, yes, I think we can conclude this webinar now. And any questions can ask. Okay. Yes, there are timing violations in Z-boot, but application-wise, the loopback is correct, and the same timing violations we saw when we were trying to use an IP integration with Z-boot for IIR filtering. So I2S transmitter and receiver, through that also we faced some issues, but it's not acceptable. But like I said, it's varies depends on application. So application-wise, we have done. Any other questions? And the thing about this timing variations is the first approach what we think is we are receiving this input in Z mode for basically noise cancellation. So you may face more timing violations when you try to implement artificial intelligence in this. We are facing, but yeah, I think we can do. The time domain and frequency domain representation was, this was the only way we did. Why? So, any other questions? Okay. Will the same procedure work for wireless image transmission as well as using userboard? Yes, it is. Yes, very brilliant question. Yes, it is possible, but you have to use AD9361 in an FMC format. So I guess AD9361, it is possible if you use AD9361 FMC COM 3. So like I said, if an FMC can send it, AD9361, it is an RF agile transceiver. So if it can send you the audio or video, you can also do the same procedure. You just have to give it the differential signals through your Z board. So it is possible and it is implementable. So I think we have implemented that. So I guess I will share you the link which is used for this. Yes. So this is what can be used for image transmission. Suppose you have to transmit an image from a USRP and you have to receive it on your Z board. So this is something which we have to use or use it in the FMC port of your Z board, AD FMC COM 9361, and it has the same FMC connector. So through a FMC connector, you can display it, and it can be used for both transmitter and receiver function in any software-defined radio. So the ADC 9361 chip is the main thing, and if that part is sorted out, I think it is definitely possible. So we have implemented. Now you will face some challenges, especially when it comes to video transmission rather than audio transmission. Is the video has to be converted into packets. The packetization has to happen. Then you can send it to this AD FMC COM. So then you can see it on the baseband or the RF front end. The digital front end should be correct and accurate. So if you do that, means from 70 megahertz to 6 gigahertz of range, you can see the data. So same what we used in our USRP B210, same bandwidth, everything is similar, just the processor will change it for you. So if you do that, that's, yes. Any other questions?
Sir, what is the difference between SDR and FMCC that got ADC 9361?
See, it's not different. Let me show you again. It is not different. The only thing that is changing is the procedure. I mean, let me show you in my slide. Both components are same. Part number is same. IC is same. Just the processor is different. This is a processor which is communicating via and RF. It is communicating or it is converting into RF, but the internal block design will be same, just like this. The FMC COM, what we are sending to an USB controller. So this you can see that USRP is something that has a USB 3 connector. This USB connector is trying to send it to the AD9361. But here, instead, when you use an FMC COM from Z board, you have to figure out how you will send this differential data as your input and how you will send and receive. So FPGA will send some differential data, these differential data inside this AD9361, and this AD9361 with respect to that, you have to receive it from your receiver. Whatever it is transmitting, you have to receive it. So this is the architectural diagram. So analog to digital converter and digital to analog converter, both are same. What you use in this is just an additional board which you can integrate in your Z board for video transmission using RF frequency.
Means that board containing HDR also, no? You are telling.
Yeah, this is an SDR. You can see the overview also here.
Okay.
It is an highly integrated RF transceiver intended for use in RF applications such as 3G and 4G base station and test equipment application for software-defined radio. The thing about what you can tell video transmission when it comes to that is once you are doing Z mode integration, you have to focus on the data whatever you are sending. This receiver port has to go through packetization of your video. So every pixel has to be converted into packet, then it will go in the RF medium. So from digital front end to RF front end, what USRP is doing is it's working on an RF front end to digital. You have to focus on the digital front end, then you can focus on the RF front end. Whereas the architecture of both will be same. Only the controller and the processor is different.
Sir, you did something right, like image you transmitted.
Yes.
And you have seen those outputs in some another application, not in WebAudio, where you have seen those output like signals. That signals
Output of signals. We have seen the JNU radio.
That is in JNU.
Yes. Video transmission we have seen in JNU radio. Because see, when it comes to JNU radio, it has a pre-bit bit file which is given from National Institutes. It is USRP. They give a pre-built image file which concludes the digital front end. We only focus on the RF front end. But if you are interested on digital front end, you have many ways where you can generate the IQ signals using DDS compiler. So this DDS compiler can generate IQ signals. You can use MATLAB also. MATLAB is a very good tool for someone who is working on SDR.